Hey guys, welcome to another episode of Learn with Sir Glenn, and for this video, we're going to discuss area of segment of a circle. So, let's go! Before we proceed with finding the area of segment, let's review first special right triangle because we're going to use it on finding the area of segment. So special right triangles are considered special because given one side of this triangle, you can easily solve for the other two sides. So there are two special right triangles. So the first one is 30, 60, 90 right triangle. So you will notice that the angles are measures 30, 60, 90. Then on the 30, 60, 90 right triangle, the shorter leg is A, the longer leg is B, and the longest leg or the hypotenuse is C. So these are special because you can easily find the other two measurements given one side of this triangle. And for this one, we can have the A is equal to 1/2 of C or C over 2 and B is equal to A squared of 3. So given a C, you can easily find A and B. Then the next special right triangle is 45, 45, 90 right triangle. So this is also known as the isosceles right triangle. Since the base angles are congruent, which are both 45 degrees, the legs of these triangles are congruent. So therefore, the longest leg or the hypotenuse is still C, and both legs are A. So for this one, if you want to solve for A, you can just simply get C square root of 2 over 2. Okay, so let's proceed with the segment of circle. So by definition, it is a region bounded by an arc and the chord of the arc. So to differentiate segment of circle and sector of a circle, let's have this diagram. So if you have a circle, let's say circle A, then radius AB and radius AC, you can have a sector of a circle. In the definition of sector of circle, it is bounded by a chord and the arc. So therefore, for us to have a segment of a circle, we will need a chord. So let's have BC as our chord. So notice that there's a small portion on our circle which is bounded by a chord BC and arc BC. And that is what you call the segment of a circle. If we're going to look for the area of this portion of the circle, we're going to have the area of the sector, then we're going to remove the triangular portion on our figure. So therefore, our formula for the area of segment is equal to the area of sector minus the area of triangle. So we can also have the area of segment is equal to theta over 360 pi r squared, which is the formula for the area of sector, minus 1/2 BH, which is the formula for the triangle. On the formula of triangle, B is the base of the triangle and H is the height of the triangle. Okay, so now let's try to use the formula in finding the area of the shaded region. So let's say you have this figure and we have your shaded region, which is obviously an example of segment of a circle. So using the formula, area of segment is equal to area of sector minus area of triangle. We will have area of segment is equal to theta over 360 pi r squared minus 1/2 base times height. Since we are going to solve for two areas here, area per sector and area of triangle, we can solve these two separately. So let's have area of sector first. So for the area of sector, we're going to use the theta, which is on our figure 120 degrees, and radius, which is 6 meters. So replacing the theta and the radius on our equation, we will have 120 over 360 pi 6 squared. Then simplifying 120 over 360, you will have 1/3. Then 6 squared will give you 36. So therefore, we will have 1/3 pi times 36. Then we can actually cross cancel 36 and 3, which will give us 12. So therefore, our area of sector is equal to 12 pi meters squared. So since we already have the area of sector, it's time to find the area of triangle using the formula 1/2 of base times height. For the triangle, we have to find first the base and we also need the height. So to find those base and height, let's have our triangle in a separate figure. So we have here your height. In the definition of the height of triangle, it should be perpendicular to your base. So notice that the figure is similar to your Radai chord theorem. So according to that theorem, If the given radius is perpendicular to a chord, then it will divide your chord into two congruent segments. So since the height of the triangle here is a portion of a radius of our circle, then we can apply that radius chord theorem on this figure. So therefore, your height will divide your base into two congruent segments. At the same time, it will also bisect your 120-degree angle. So therefore, the measure of angle here is 60 degrees, and so with the other angle. So now, we have here two triangles, and we can actually find the missing angle on our triangle since the sum of the three angles on a triangle is 180 degrees. So we already have here 60 degrees, and the perpendicular will form a 90-degree angle. So therefore, the remaining angle on the top of the triangle is 30 degrees. Then we also are given here the radius, which is 6 meters. So to easily find the base and the height of our triangle, let's just simply work on one of the triangle. And notice that this triangle will form a 30, 60, 90 right triangle. So in the 30, 60, 90 right triangle, your R will become your C, which is equal to 6. Then your height, which is the blue segment, is our A. Then the half of our base will be our B. So since this is 30, 60, 90 triangle, in the 30, 60, 90 triangle, if you're given the C, you can get the A by getting 1/2 of C. And you can get the B by getting A square root of 3. So in our figure, since C is equal to 6, 1/2 of that is 3, which is our A. Then since we already have the A, we can easily get the B by replacing A in A square root of 3, and that will give us 3 square root of 3. So now we already have the values of A and B, we can now put it back on our original figure. Each portion of your base is equal to 3 square root of 3. So therefore, your base is equal to 6 square root of 3, combining the 3 square root of 3 plus 3 square root of 3. Then for the height, so that will be your A, which is equal to 3 meters. So after finding the measure of base and height, we can now use the formula to solve for the area of triangle. And that will give us 1/2 of 6 square root of 3, replacing the base, times 3, replacing the height. Then multiplying this expression, we will have 1/2 of 18 square root of 3. Then getting the 1/2 of 18 square root of 3 will give you 9 square root of 3 meters squared. So we already have the area of the sector and the area of triangle. We can now find the area of segment by subtracting the area of sector minus the area of triangle, which will give us area of segment is equal to 12 pi minus 9 square root of 3. Since we cannot combine this expression unless we express this expression in decimals, we can just simply leave it as is. So therefore, we will have area of segment is equal to 12 pi minus 9 square root of 3 meters squared. Okay, so let's have another example. Find the area of the shaded region, which is an example of a segment of a circle. So the same with the previous example, we're going to use the formula as area of segment is equal to area of sector minus area of triangle. Or we can have area of segment is equal to theta over 360 pi r squared minus 1/2 base times height. Going to solve for the two areas separately. So let's have the area of sector first, which is theta over 360 pi r squared. So for this one, we're going to use the theta, which is 90 on the given figure, and the radius, which is 4 cm. So replacing the values of theta and radius, we will have area of sector is equal to 90 over 360 pi 4 squared. So simplifying this further, we will have 1/4, which is simplified form of 90 over 360 pi times 16, which is 4 squared. So after this, we can cross cancel 4 and 16, which will give us 4. So therefore, our area of sector is equal to 4 pi cm squared. Now let's look for the area of our triangle. So again, the same with the previous example. For the area of triangle, we have to find the base and the height of our triangle. And to do that, we can separate the triangle from our figure for the ease of finding the values of base and height. So again, your height is perpendicular to your base, which will divide your base into two congruent segments at the same time bisecting your 90-degree angle. So therefore, the measure of your angle will become 45 and 45. Then using the concept of interior angles of triangle that will sum up to 180 degrees, we can find the other angle here which is also 45 degrees. Then given the radius which is 4 cm. So to easily find the measure of base and height, let's focus on just one triangle. So notice that this triangle will form a 45, 45, 90 triangle. And on this one, your R will become your C, which is the hypotenuse, which is equal to 4. Then both legs will become A. So in the 45, 45, 90 right triangle, given the C, we can easily find the A by getting C squared of 2 over 2. So since our C is 4, we're just going to replace C on our equation, and that will give us 4 squared of 2 over 2. Simplifying this will give you 2 squared of 2. And so with the other A, 2 squared of 2. Since we already have here the value of the height and the value of the half of your base, we can now put it on our original figure. So therefore, our base is the combination of 2 squared of 2 and 2 squared of 2, which will give us 4 squared of 2. Then our height is the measure of the A in our 45, 45, 90 right triangle. So that will give us 2 squared of 2 cm. So using these values, we can solve for the area of triangle. We will now have 1/2 of 4 squared of 2 times 2 squared of 2. Then after this, we will now have area of triangle is equal to 1/2 of 16. Simplifying this, we will have area of triangle is equal to 8 cm squared. Since we already have the area of sector and area of triangle, we can now find the area of segment by subtracting the area of sector minus the area of triangle. And that will give us 4 pi minus 8. Our area of segment is equal to 4 pi minus 8 cm squared. So okay, that's it. Thank you for watching and hope you have learned something from this video.